Hello, I'm Leon, and today I'm going to present you Root Shield, which is predicting weather impact delivery routes using deep learning. We also partnered with Eva Castro on this, who's an in-person student, and Sriya Tumbala. In terms of motivation, why we did this project, the weather events disrupt logistics, causing delays and safety risks. So operators often lack proactive routing intelligence. So we frame prediction as binary classification for pre-dispatch risk decisions. Uh, in terms of data set and labeling, the way we built this is we built our data set by joining NOAA, California Storm Records, with about 20,000 synthetic delivery routes that we created. Each route receives an engineered severity score based on storm type, magnitude, causalities, and damage, and then routes with a score of greater than 0.25, which is the impact score, are labeled as impacted. Why the scoring? The severity function embeds domain knowledge. Instead of forcing neural networks to discover hazard physics from scratch, we encode operational heuristics explicitly. In terms of baseline models, as you can see in the poster, the severity function, logistics regression validates linear separability. The random forest then allows nonlinear splits to detect interaction effects with deep learning. The model architecture that we chose is we have our multi-layer perceptron, so the MLP architecture designed to evaluate whether deep learning could extract predictive structure not captured by engineering score. So if the deep learning can capture more stuff that we put into the scoring already. For the architecture, we have an input layer. It's a vector including route length, country, county, encodings, and impact features. With a dense layer of 1 to 64 neurons with a ReLU activation, which learns nonlinear features transformations. Dense layer of 2 to 32 neurons with a ReLU, which compresses learned interactions. A dropout that randomly deactivates neurons during training. Interactions, and an output layer with a sigmoid activation function that produces the probability of the root disruption. For the training details, I'll just go over this super quickly. We have, for the loss, we have a binary cross entropy to penalize misclassification. For the optimizer, we used Adam for efficient gradient updates. The batch size is 32, balancing stability and computational efficiency. And the early stop, and then we have early stopping, which monitors a validation loss to avoid overfitting. For the weight initialization, we initialized compatible with ReLU layers. In terms of interpretation, the MLP allows representation learning, so the network can discover combinations of geography and severity patterns. However, the results show it largely validates the engineered scoring function instead of discovering fundamentally new signals. For the ablation study design, Model A as a full features, including severity score. Model B is a geography only with single county, and Model C, multi-hard route geography without a score. Why do we use these ablations? A test correctness. A tests the correctness of the scoring. B stress tests the geography, obviously, which is important, and C tests whether the structural root encoding actually allows neural inference of the score logic. In terms of result summary, for Model A, the upper AUPRC is 1. For Model B, it's 0.662, showing a weak geographic signal, actually. And then for Model C, it's near A, suggesting that the root structure compensates for the missing score. In terms of interpretation of that, the deep learning, I mean, it basically says that deep learning validates the engineered scores. So geography alone is insufficient. The root structure adds predictive value, but the severity score remains predominant. And then in terms of scientific insights, what that means is that this really mirrors real systems. The engineered risk score functions outperform naive deep learning whenever human heuristics already encode causal structure anyway, which makes sense in a simple model like this. Future work that could be interesting on this could be to build an integrated temporal storm propagation, have a distance-based geospatial joints, or richer root geometry and live alert ingestion, which might maybe then overcome something like this engineered risk scoring functions that outperform the native deep learning. Yeah, that's our model. We look forward to deploying this in operational routing engineers. Thank you.